Hey, good afternoon, and in today's video I will solve exercise 6 of module 5, which is called Queuing Theory. And without any further ado, let us commence. The exercise tells us that there is a switch that receives packets from 10 different computers that must be forwarded to an upper node in the network. The packet lengths are exponentially distributed with min 960 bits. Each computer generates packets following a Poisson distributed with min lambda 2.5 packets per second, and we have to assume that the switch and the upper node are connected by a 64 kilobits per second link. We have to compute the average time to transmit a single packet by the switch, the probability to have no waiting time by a packet, and the average waiting time in the queue. So, as you can clearly see, I have already done some schematics of the data that the problem tells us. In question A, in part A, we have to compute the average service time per packet. We know that lambda in each of the cases is 2.5 packets per second, and there are 10 computers, so it will be 10 times 2.5, which equals 25 packets per second. I will need this data further on, and now x, we have to get the expected value of x, and x is an exponential random variable, so it will be the division between the average packet length divided by 64 kilobytes per second. So the expected, this is because it's a an exponential random variable, and ex equals el divided by the 64 kilobytes per second, and 960 divided by 64 times 10 to the power minus 3 to the power of 3, equals 15 milliseconds, and we got to obtain mu. Mu is the inverse of the expected value of x, so answer to the minus 1, it will be 66.6 period packets divided by second. Okay, now what's the probability to have no waiting time in the packet? So, knowing that it is a case of a queuing theory problem of MM1, P must be equal to lambda divided by mu. If we calculate this, it will be 25 divided by answer, so 3/8, and P0 will be 1 minus P, so it will be 5/8, and 1 minus answer, just to check what must be equal in decimals. And now we gotta obtain the average waiting time in the queue. So the expected value of n equals p divided 1 by 1 minus p, then et will be equal to en by lambda, which is the same as 1 minus mu minus lambda, and the average waiting time will be this. Okay, so we could solve this, or we can just simply do this. I will do the average number just in case. So 3/8 divided by 5/8, which gives 0.6, and E over T will be 0.6 divided by lambda, so 0.6 divided by 25, and should be equal to 0.024, and for this would be 24 minus 0.015, which is 9 times E3, or the same as in microseconds. This is 24 microseconds, and this is the end of the video, and stay tuned for the next ones.